Every time you press the accelerator, you trigger a controlled explosion powerful enough to move a ton of metal, yet precise enough to repeat thousands of times a minute without tearing the engine apart. But what actually happens in those split-second bursts? Let's break open the engine's secrets. You know, when you pop open the hood of a car, it might look like a maze of metal and wires. But at its core, a car engine is basically a controlled explosion machine. And that's honestly what makes it so cool. Every time you press the accelerator, you're telling the engine to burn fuel faster, create more tiny explosions, and push the car forward with more force. It's wild when you think about it. Chemical energy from petrol getting converted into motion, thousands of times every single minute. But why does every modern car engine, no matter the brand or horsepower, still rely on the exact same rhythm invented over a century ago? You see, most modern engines follow something called the four-stroke cycle. It's been around for more than 100 years, first imagined by Alphonse Baud de Rochat, and later perfected by Nicolaus Otto. Which is why we often call it the Otto cycle. And here's the fun part. Even with all the fancy tech in today's cars, this basic cycle hasn't really changed. It's reliable, efficient, and just works. Now let's look at the engine's basic layout. At the center, you've got the engine block. The big solid chunk of metal, usually made from cast iron or aluminum. Think of it as the engine's skeleton. Inside the block are the cylinders, which are basically smooth metal tubes where the real action happens. These cylinders hold the pistons, and the pistons move up and down like the heartbeat of the engine. To keep everything cool and smooth, the block also has passages for coolant to flow through and channels for oil to lubricate all the fast-moving parts. Without these, the engine would overheat or seize up in no time. On top of the block sits the cylinder head, almost like a lid packed with important hardware. This is where you'll find the valves, which open and close to let air and fuel in and push exhaust gases out. The spark plugs are also here, waiting to ignite the fuel-air mixture at just the right moment. And with modern engines, fuel injectors spray in fuel with pinpoint accuracy. Now, imagine the engine as a living machine. The piston is basically its muscle, constantly firing, moving, and putting in the real work. It shoots up and down inside the cylinder, thousands of times a minute, pushed by the tiny explosions happening during combustion. Every rise and fall of that piston is synced with fuel, air, spark, and exhaust. But the piston can't do the job alone. It's connected to a long, sturdy arm called the connecting rod. It's like your forearm linking your hand to your shoulder. This rod transfers the piston's straight up and down movement to the crankshaft, the real hero that turns all this motion into something useful. The crankshaft sits deep in the engine block and spins with incredible force. It's built from tough steel or iron because it has to survive the brutal power of combustion, hitting it again and again. So what's the secret inside your engine that turns those wild up and down piston punches into smooth rotation? Well, here's the surprise. The crankshaft transforms that straight-line piston motion into rotation. That rotation eventually travels through the transmission, the drive shaft, and finally reaches the wheels, making your car move. Every bit of acceleration you feel on the road traces back to this conversion. Now let's talk about the magic behind it all. The four-stroke cycle. Modern engines are insanely efficient because this cycle happens so quickly and so precisely. One full cycle needs 4 movements of the piston: intake, compression, power, and exhaust. And while this is happening, the crankshaft completes 2 full spins. Imagine that repeating thousands of times per minute. That's the rhythm of your engine. The first part is the intake stroke. The piston sitting at the top is called the top dead center, or TDC. As it moves downward, the intake valve swings open. This creates a vacuum that pulls in a perfectly balanced mix of air and fuel. In petrol engines, the ratio is roughly 1 part fuel to 15 parts air, though modern fuel injectors make this even more precise by spraying fuel directly into the cylinder. By the time the piston reaches bottom dead center, the cylinder is filled with this explosive mixture. About 10,000 gallons of air for every gallon of fuel. Then the intake valve closes, locking everything inside and setting the stage for the next big moment. Compression. Alright, now we're getting into the part of the engine cycle that really shows you how smart and powerful this whole system is. After the piston pulls in the air-fuel mix, it immediately begins the compression stroke. This is when the piston pushes back up toward the top of the cylinder and both valves stay completely shut. No air coming in, no gas going out. Just the piston squeezing that mixture tighter and tighter. By the time it reaches the top, the volume is reduced to almost 1/8 of what it was. And trust me, that squeeze is important. When you compress the mixture like this, you raise its temperature and pressure, making it way easier to ignite and burn efficiently. That's why high compression engines feel so strong. They get more bang out of the same amount of fuel, simply because the air-fuel mix is more tightly packed. Now comes the moment every car lover gets excited about, the power stroke. As the piston reaches the top, just a breath away from top dead center, the spark plug fires, and it's a jolt anywhere between 5,000 and 40,000 volts. That spark ignites the compressed mixture, but here's the cool part. Combustion doesn't happen instantly. It actually burns across the chamber in a controlled, timed sweep. This timing is everything. The spark needs to fire at precisely the right angle before the piston reaches the top, what mechanics call degrees BTDC, or before top dead center. If everything is timed perfectly, the explosion hits maximum pressure around 20 degrees after the piston starts moving down again. That's the sweet spot. At this point, the expanding gases slam the piston downward with incredible force, spinning the crankshaft and delivering the power you feel when you accelerate. And during this stroke, both valves stay shut tight, trapping all that explosive force inside the cylinder. Finally, we hit the exhaust stroke. The piston reaches the bottom and starts heading upward once more. But this time, the exhaust valve opens. The rising piston pushes out all the burnt gases. The smoke of that mini explosion through the exhaust system. Just after it crosses the top again, the exhaust valve shuts, the intake valve opens, and the whole beautiful cycle starts all over again. When you really get into how an engine works, one thing becomes obvious. Timing is everything. Even the most powerful engine would be useless if its parts didn't move in perfect sync. That's where the timing and control systems step in. At the center of this is the camshaft. A long rotating shaft with these funny egg-shaped lobes on it. As it spins, those lobes push against followers, which move push rods and rocker arms, opening and closing the valves with millisecond accuracy. And the camshaft is driven by the crankshaft through a timing belt, chain, or gears. It always rotates at exactly half the crankshaft speed, keeping valve movement perfectly matched to the piston's motion. Modern engines take this even further with variable valve timing. This tech adjusts the camshaft angle depending on how fast you're driving or how hard the engine is working. Need power at high RPM? The valves open earlier and for longer. Cruising at low speed? The timing tightens up for efficiency. Then comes the heart of combustion, the air-fuel mixture. The perfect chemical balance, called the stoichiometric ratio, is about 14.7 parts air to 1 part fuel for petrol engines. At this ratio, everything burns cleanly. But engines behave differently depending on the mix. If you want maximum power, you run a bit rich, around 12.6 to 1. More fuel? Bigger boom. If you want mileage, you go lean, around 16 to 1. Less fuel? Softer burn. Today's computers constantly tweak this ratio on the fly to match your driving style. Now, why stick to the 4-stroke cycle when 2-stroke engines are simpler and make a power stroke every revolution? Because 4 strokes are cleaner, smoother, and more efficient. They push exhaust out more effectively and refill the cylinder with fresh air and fuel without wasting it. That's why your car engine lasts longer, burns cleaner, and gives better mileage. At the end of the day, a car engine is a beautifully engineered machine. A mix of mechanical brilliance and electronic intelligence. Every spark, every valve movement, every piston stroke happens with incredible precision. And this coordination, perfected over more than a century, is what makes the internal combustion engine one of the most impressive inventions ever put on wheels. So what do you think? Which part of the engine cycle blew your mind the most? Or did we miss your favorite detail? Drop it in the comments. And hey, if your pistons are firing and you're still watching, hit that subscribe button. Unless you're secretly a two-stroke engine. In that case, we totally understand.